بسم الله الرحمن الرحيم، والصلاة والسلام على سيدنا رسول الله وعلى آله وصحبه أجمعين. نرحب بكم جميعا ونكرر اعتذارنا عن التأخير الغير مقصود. وبسم الله نبدأ. ستكون المحاضرة الأولى يلقيها عليكم الدكتور حمود المحمدي من الجامعة الإسلامية في كلية الهندسة، قسم الهندسة الكيميائية، بعنوان إنتاج الوقود من مخلفات البلاستيك، دراسة تحليلية. وستكون مدة المحاضرة ربع ساعة، وسيتاح إن شاء الله باب الأسئلة في نهاية المحاضرات الأربعة. رحبوا معي بالدكتور حمود المحمدي، فليتفضل مشكورا.
السلام عليكم ورحمة الله وبركاته. If you allow me, I'm going to talk in English because my slides in English, but I'll try to mix it English and Arabic. If that's good with you. First, I would like to thank هيئة المهندسين السعوديين for organizing this event, and for me, this first time to present such some materials and this kind of platform. My presentation today, inshallah, about the producing hydrocarbon fuel from the plastic waste. We're going to talk about the techno-economic assessment because I'm not going to go with more details, technical details. I'm trying to matching between technical details and economics studies. First, as you know, we have solid waste in Saudi Arabia and all over the world. One of them is plastic, and we throw it away, and which is kind of not acceptable. And here in our project, we try to just emphasize why is using the plastic waste is valuable to producing the hydrocarbon. First, to managing the solid waste, we have to go through steps or first, we have source reductions. We have to minimizing using the solid waste as much as we can. Second, reuse it or recycle it. Reuse it again. If you cannot reuse it, okay, recycle it. Either plastic or metal or whatever. Then convert it to energy. If you cannot recycle it, convert it to energy. At least get a valuable product from the waste. Or compose it. The last thing is dumping it in the landfill. Recycling, every day we're using material that's made from recyclable materials. As you know, if you can see your tables, all the stuff around the tables, it can be recyclable. Just as glasses, cans, and newspaper, paper, whatever, can be recycled and also can be used as a raw materials for different products. Like for our project today, using the plastic waste as a raw materials for producing the hydrocarbon fuel. Waste to energy, as you know, is trending now around the world, using the waste to producing energy, and also about the circular economics. We have different type of process that can be used to converting the waste to energy. For example, we have pyrolysis process at high temperature from 500 to 700. We have gasifications, and we have liquefacions, and we have fermentations at low temperatures. And each process has advantage, disadvantage, and each process is suitable for different materials and what you are looking for as a final product. For example, for our study today, we're going to use a pyrolysis process for producing the hydrocarbon fuel. First, let's talk about the solid waste in Saudi Arabia. We have a populations of 35 million, and we're producing about 15 million tons per solid waste. And all the landfills in Saudi Arabia is gonna reach to the maximum capacity in 10, 20 years. Okay? And we have to take an actions. And also for recycling the materials, we have just from 10 till 15% from the materials is recycled right now. And also we are in the aerial stage for recycling. So one of the process, okay, maybe we can invest in this recyclable materials or this valuable materials and what is a product to convert it as energy. And this is going to be our study today. First, let's talk about the fast pyrolysis. Maybe some of you know about this process, some of you just heard about it. It's a process to convert the solid, mass solid, to liquid product in absence of oxygen. And has a very resistance time, it just go right away with high temperatures and an atmospheric pressure. And as you know, we have the product goes to the biomass. Here we have an example for the biomass feed. We have the pyrolyzer. Then we have a product as a gas because we have high temperatures. Then we have the cyclone to separate the char and the solid product from the gas. Then we're gonna condensate the gases to have two phases, which is gas and liquid. Gas, non-condensable gases like methane and light hydrocarbon, and also we have a liquid as bio-oil. This is just an example how it's the fast pyrolysis process. In our study, we're trying to matching if you would like to producing the hydrocarbon fuel from the plastic waste, how much it costs, how much the profit. Is visible process or not? This is the main idea about our study today. We're using the Aspen Plus. I know 100% most of you heard about the Aspen Plus, how to use it, and which is powerful tools for the chemical engineering in general. We plan to, the plant assumed to process 1,000 dry metric ton of plastic waste. 40% is gonna be polystyrenes, 20% polyethylene, and polypropylene is gonna be 20%, and 20% gonna be PET. And we try to mix the waste plastic as a mix between other kind of plastic, okay? Because some kind of plastic has a high yield, some of them it has low yield on the hydrocarbon fuel, but we have this mix based on what? The average of the, in general, solid plastic waste in Saudi Arabia, okay? Then we estimate the energy requirement for this process. It's visible or not. We're reaching the mass and energy balance for this process or not. Then we do the equipment sizing. Then we calculating the minimum selling price for selling this product. Here we have the block flow diagram for the process. First we have the pre-treatment, which is crushing, first washing the plastic, then dry it, then crush it in order to have it in the pyrolysis. Then we have pyrolysis, and the process we have three main products. We have gases, it's gonna be used for the hydrogen productions because we need the hydrogen for upgrading the oil, okay, in order to produce the hydrocarbon fuel. Then we have the oil, okay, it's gonna be fed to the upgrading step. Then we have the char. We need the char to provide the heat for the reactors because the reactor is 500 degrees and need heat, okay? We will not use the electricity or any other heat resource, so we're gonna burn the char even though the char is variable. Maybe we can produce catalyst, active carbon from the char. A lot of studies about using the char as a base catalyst or supported catalyst or whatever. So, but in our case, we're gonna use the char as a source for the heat. We're gonna burn it and provide the heat for the pyrolysis. Then we have a product from the hydrogen productions unit, and we have the oil. It's going to mix together in this upgrading step. Then we have some gases from that unit. We have oil and we have gases as well from the upgrading step, and we're going to use the gases for power generations. And as you can see, we did this calculation in the mass and material, mass and energy balance, and it's very well balanced. And even we have extra electricity and extra power, we're gonna sell it for the grid, okay? We model the process in the Aspen Plus, and we have experimental result. As you can see, the carbon and hydrogen oxygen content in our feed. We have 83 carbon, 7 hydrogen, and 10% oxygen. And the heating value for our feed is going to be 38. The heating value, if you compare it with the hydrocarbon fuel is around 45 till 50, the heating value. And we put this experimental result in the Aspen. And also we have gases, experimental results as gases with this percentage, 73 carbon, 20 hydrogen, and 7 oxygen. And as well we put in the Aspen as the CO, CO2, hydrogen, and methane, and ethane, and so on. Also we model the upgrading oil to feed and using the steam reforming to generate the hydrogen. All of you know what is the steam reforming process. It's just the gas methane with the CO and CO2 to convert it to hydrogen. And then we have BSI to separate the hydrogen. Then we use the hydrogen for the hydrotreating reactor to upgrade the oil. In our oil, we have 10% oxygen. We have to remove the oxygen from the oil, okay? And all the hydrocarbon, the percentage of oxygen, it's 0. Then we do the hydrotreating by hydrogen and the catalysis. We have nickel silica ammonia with 35 degrees Celsius and 750 psi. Then from this step, we're producing the hydrocarbon fuel, and then we separate it to gases. It's going to go to the power. And also we have water because we convert the oxygen to water by using the hydrogen. Then we have the hydrocarbon fuel. Then we have the process to produce the yield is 36% is the hydrocarbon fuel, 41% is the gas, and 5% is the water, and 18% char. And we produce from this process 35 million ton, which is equal to what? 66 gallon per dry metric ton of plastic waste. Each metric ton of a plastic waste is going to produce 66 gallons of hydrocarbon fuel. And the hydrocarbon fuel is low due to the high yield of gases because most of our feeds compared to the gases and char. And we use the capital cost assessment to see if we would like to produce this oil and this product, how much it's going to cost. We have some assumptions. We have the plant size is 100,000 metric ton, interest rate 10%, depreciation is 7 years, and so on. And we have these assumptions as all that is known worldwide. A lot of publications paper use the same assumptions because we're going to compare about our study with other study. So we have to use the same assumptions. From these assumptions, we have the capital investment as the pre-treatment is going to cost 8.5 million. Pyrolysis is going to be 13 million. upgrading and separation, 24 million. Hydrogen production, 7 million. Energy generations, 6 million. Water cooling is going to be reach 6 million. And the total installed equipment, it costs how much? Around 65 million. From this, as you can see, the total capital investment in total with land and site development and all working capital, all of them is going to be reached up to how much? 118 million. So to processing 1,000 of dry metric ton of plastic, you have to invest 118 million in that plant. As you can see, 58% is going to be pyrolysis and upgrading step. It costs around 58% from the total process. And now we calculate the capital investment. Now we have to calculate the operation cost, the feedstock, how much it costs. Catalysis, 1 million. Utilities, 4 million. Waste treatment, 2 million, and so on. The total cost of production is 26 million. Here we put the feedstock is 0. Why? Because it's waste. It doesn't cost anything for the owner of the plant. Okay? And it's going to be producing from 1,000 dry metric ton of plastic waste. Project to produce 43.2 million gallons of transportation fuel per year. So we have some assumptions, okay? Now, how are we going to verify your assumptions is valid or not? Because, okay, we assume that feedstock is 0. How about if I have to pay $20 per ton? How much the price is going to be changed? If I have to pay $20 per ton, the price is going to, first, the selling price is about 0.6 USD dollar per gallon, okay? Which is very good the price. Below the price now here in Saudi Arabia, per gallon, okay? Which is make the project is profitable and you have a lot of revenue and from this project. But how we're gonna verify our assumptions? If I have to pay $20 per ton, how much it costs? It's gonna cost around 83 cents per gallon. How about if the government, they pay me $20 per ton to remove it, okay, from the site? They're gonna pay me 20 per dry metric ton. It's gonna be reach about 43 cents. The plant capacity also has the measures. Maybe our assumptions for calculating the accumulating size is not good. How about if the plant capacity is 2,000 dry metric ton? It's gonna be go to, because if increasing the capacity, you're gonna decreasing the capital investment in general. Okay? If you're increasing the plant capacity 2,000, the price is going to be go to up to 33 cents. How about if I decreasing the capacity? How much it affects in the final product? It's going to be reach up to 78. So from this, we can see the capacity of the plant. It's very sensitive. Okay? And also distribution and selling is also contributing. It's not that much. As well the capital investment. Also the capital investment, even if our calculations have 30% is not accurate, the price is going to be reached about 73. It's just different 3 cents. 2 minutes? Okay, I'm going to make it fast. And also when we have the capital investment, here we're going to see how affect the yield of the hydrocarbon and the minimum selling price. Okay? As you can see here, as the yield is increased, the price is decreased. Okay? And the yield is depend on what? And the type of the plastic waste. If you have polystyrene, it's different than polyethylene. It's different than PET. So as the yield is increased, the price is going to be decreased, reach up to 30. And also, if you have a yield of 10%, you're going to sell it by 1.7 dollar per gallon. But if you have 30, you're going to reach up to 30 cents. I'm going to conclude my presentations by the plant assume is 1,000 diametric ton. We have this type of plastic. The mass and energy yields is 36 as a mass yield. From the total yield, 36 is going to be hydrocarbon fuel. How about the energy? We're going to have 42 as the energy yield. As we said, the low mass yield due to we have other products, gas and condensable gases and char as well. The capital investment for this project in 118 million and the production cost 27 million. The minimum selling price for the project is for 20 years. It's 60 cents per gallon. And also we do some sensitivity analysis to show you how sensitive our assumptions to the minimum selling price. And also we're going to do further research and development for the plastic waste in this project. And also if you would like to contribute with us in this project, or if you like it, interested, just you can reach us in this email. And thank you for your listening.
شكرا دكتور حمد على المحاضرة الجميلة. المتحدث الثاني دكتور أرشد محمود علي من كلية الهندسة جامعة الملك عبد العزيز بجدة بعنوان نزع الهيدروجين التحفيزي النشط للغاية أو الانتقال للمستفز. بس أعطونا المحاضرة الثانية. أرشد على الأساس. قبلنا بتطلع في الشاشة.
Assalamu alaikum and good morning, everybody. Thank you so much for inviting me here and to give me an opportunity to share our recent experiences to develop a catalyst to produce butene isomers. So the titles of this talk, I'll keep myself simple. I will not go into that details because of the short of time. So let's begin the journey. Okay. So before I go into detail, I would love to introduce myself and my research groups. I'm working in 4 areas, and number 1 is heterogeneous catalysis. And there are few universities where we are lies up in an intensive way. It includes King Abdulaziz University, Soja University, University of Technology, Petronas, Malaysia. And another work we are working is environmental catalysis. And my partners are here is King Abdulaziz University, UTP, and University of Auckland, New Zealand. And the third area we are focusing is sustainability. And again, I'm glad to have a collaboration with the European universities like Brno and Hamad bin Khalifa University, of course, KU and University of Technology, Petronas, and ComSat from Pakistan. And the last area where we are working is process safety management. And let's begin with so far this research output produced 79 publications and 1 online patent, and 1 patent is filed. Hopefully we'll get it soon. And let's come back to the talk. the dehydrogenation of N-butane to butene isomers. This is the team which work in this project. I'm very glad to have such a wonderful team like Professor Abdulrahani, Professor Petrov, Professor Daus, and Dr. Sitaram Padilla and myself. And this work was done with the generous facilities we have at Heterogeneous Catalysis Group at Chemical and Material Engineering Department, King Abdulaziz University. And these are the goals which we'll talk about. I will go quickly the background of the talk and the project's goal which we set and the project's goal which we achieved and what we are aiming for the next and the path forward. Let's go. The background is that the butene isomers, they are like few in numbers, like 1 butene, 2 butene, isobutylene, and butadiene. And this is the total word consumption of these butylines. And approximately 81% goes to fuel market, and 18.5% goes to the chemical uses. If I go to the chemical use, let's talk about the fuel market. The fuel market, they are methyl tertiary butyl ethers and ethyl tertiary butyl ethers. They are used as a gasoline blend. And the next is linear low density polythenes or polyethylenes or polybutylenes or butylene oxides or C4 solvents for different usage. The current approach for such studies are 4 different approaches. First one is oxidative catalytic dehydrogenation, and the second is electrocatalytic dehydrogenation, and third is CO2 oxidative catalytic dehydrogenation, and the last one is the direct catalytic dehydrogenations. This was the most studied. The oxidative catalytic dehydrogenation is one of the mostly studied point, and people pay lesser attention to the middle two, electrocatalytic and CO2 oxidative catalytic dehydrogenation. And this is the path we proposed and we opted, which is direct catalytic dehydrogenation. And we are competing ourselves with as close to as Olefix from UOP. And these were the project's goal we set for, that we would love to produce a highest yield based on highest conversion and highest selectivity. Either it can be custom made, it can be tailor made. But in doing so, we make sure that we have a very stable catalyst and we should have an easy catalyst regeneration process. And the catalyst is based on platinum sported on gamma alumina or alumina. And so in brief, in depth, I will go with that. When you need to design a catalyst, you need to work very carefully that what should be the catalyst recipe. When I'm saying catalyst recipe, you need to look at the sport, what are the key ingredients, and what are the promoters, and what are the anti-coking agents, if there is a coking involved in that process. And we follow different preparation protocols, and in this studies, we conducted 3 different preparation protocols. One was wet impregnation, another was chelation approach, and third, which we call ourselves, is a modified impregnation 1 and modified impregnation 2. And the experimental we conducted by using a microactivity PID reactor. At the moment, I cannot show you the details of the experimental setup because the patent is under file. So let's talk about, then we will talk about the catalyst life and then how we can regenerate the catalyst. So if you look at this, the first 3 tasks is almost completed. And the 4th one we are working, it is somewhere like 85 or 80, 90% you can say it is achieved so far. So let's talk about the first thing, that this is the catalyst we are producing, that we will add some promoters to our base catalyst, which is platinum gamma alumina oxide, which is you can call gamma alumina. And we use certain GHSV, and weight of the catalyst was 5.5 grams. And let's talk about the comparative study of the catalyst. If you look at on the left side, we are comparing the sport, which is gamma alumina, and then we are comparing a platinum tin sported with gamma alumina, and then we are adding a promoters, which is calcium, zinc, and calcium, zinc together. Look at the conversions. if you look at the conversion, the initial conversion of the sport is very low, whereas if you look at the last catalyst, which is platinum 10 calcium zinc, it's showing you 42.5% conversion. Now, there may be a question, people may ask us that why calcium and zinc only shows highest conversion. Well, let's go with the further selectivity. Look at the selectivity area. Why we are saying that calcium and zinc are best? Because of the selectivity, which is 94.9%. And it gave us a best yield, which is 40.3%. Now, we conducted similar experiment at 4 different temperatures. And if you look at, there were 550, 575, 600, and 625 to optimize the reaction temperatures. And based on this study, we figured out that the best catalyst composition could be platinum 10 calcium zinc, sport-on gamma alumina, which shows us approximately 51% conversion with 83.6% selectivity and giving us a very good yield of 43% based on the certain temperature. And this values I'm reporting at an optimized reaction temperature, which is 575 degrees centigrade. Now, let's see the comparison of different sports which we can build up. And here in industry, people are using multiple type of sports, but we opted gamma alumina, normal alumina, and zeolites. And we use the same catalyst with the same GHSV, and then we compared the results to make sure we are on the right track. So if you look at this comparison of gamma alumina or N alumina or zeolites, you see the conversion. Apparently, the conversion of our catalyst, platinum 10 calcium zinc, is lower as compared to zeolite, but look at the selectivity and yield. So that is why the zeolite is not good in this study. So we opted gamma alumina based on selectivity and yield, which was very good. Same, we repeated these experiments at different temperatures, and these temperatures shows you that how we can optimize. And based on this, we ended up that, yes, the best sport which we can use to build up this technology is gamma alumina, and it shows 51% conversion, 83% approximately selectivity, and 43% yield. And the third milestone which we achieved to develop this catalyst is we tried different methods for the catalyst preparations, and by using the best catalyst so far, we opted at this, I'm reporting 4. One is impregnation, which is wet impregnation, and then followed by the chelation, and then modified impregnation 1 and modified impregnation 2. And these are the conversion and selectivity and yield of these 4 different preparation protocols. And we conducted a similar experiment at 4 different temperatures and ended up with the conclusion that the best method is wet impregnation 2, which shows us a conversion of almost 67% conversion and with a 77.3% selectivity with a better yield, 52.5% yield.
5 minutes, Doctor.
And now, okay, so let's go to the further to build up the impact of the promoters and the long-term reaction time. So we added some promoters like 10 gallium, zirconia, and indium. And then the same comparison over there, and based on this comparison, we ended up that the best catalyst we have is, best catalyst is required where we have tin and indium together, which gave us a conversion of around 71% conversion with 74% selectivity and 52% yield. Now, the 5th milestone is that when we added indium, we were so much excited that it played a very good role to increase a very good bonding between platinum and tin. So they have a better platinum dispersion particles. So we try to optimize that proportionate. We conducted this study at different composition of indium, which varies from 0.5% to 3%. And we conducted the similar experiment and ended up on the conclusion that the best catalyst we can use is with indium is they have 3%, 2% based on the custom-made requirement. And in journal, it was concluded that conversion increased with the percentage increase in the indium. Same goes with the selectivity and yield. And then finally, we conducted some experiment time on stream, so to see what is the catalyst stability by using our best catalyst, which is 3% indium. And I'm reporting you this result up to only 40 hours, but we have a study even 100 hours approximately. So this shows that the conversion was very stable and the selectivity in a very good range, and the yield was almost stable under the range of 55. So based on this, we can say that we have a very stable and highly active and selective catalyst for the production of N-butane to N-butenes. And the last is, these are the milestones which I discussed so far in these presentations. And so what is our future aims? Future aim is that we would love to go further for the regeneration studies and the kinetic studies by using our base catalyst. And I'm glad to hear that this project is streamlined with the Ministry of Energy. They have shortlisted to take it to up to TRL 9. So hopefully soon we'll start this project up to TRL 4 further on, inshallah. And the future ideas we are working with this is that how we can convert ethane into thalines, or how we can extend this current project to other lower alkanes. And I also have one more idea, which it's a very I would say it's a very early stage, which is utilization of CO2 to produce biodegradable polymers. Hopefully we'll be able to build that. And thank you so much for giving me the opportunity. Thank you.
نشكر سعادة الدكتور أرشد على المحاضرة القيمة. المتحدث الثالث الدكتور ماجد عبد القادر العمودي، دكتور في جامعة الملك عبد العزيز بجدة كلية الهندسة، بعنوان تأثير حموضة المحفز على هدرجة تقرير الأوليفينات المقترحة. فليتفضل الدكتور ماجد مشكورا.
Assalamu alaikum wa rahmatullahi wa barakatuh. I would like to thank the Saudi Engineering Society for inviting me for this opportunities and giving me the chance to share my humble experience in research. I'd like to talk today about the NEMOS, or the influence of NEMOS catalyst properties on the hydrogenation and dimerization of conjugated olefin, which is mainly the heavy oil treatment. This is the outline for what I'm going to talk about today. This is the background, give you a little bit talk about the background of the oil sand or the heavy oil. And then the study objectives, why I'm doing this study. I will touch upon the catalyst preparation and the characterization of that, and then the experimental setup and the procedure. We will test these catalysts to see the catalyst activity, and finally I'll conclude what the findings of my research. Oil sand. So let me talk about this. The oil sand deposit covers more than 6 million hectares. This is a huge amount of oil sand that needed to be treated. As for the production, for now, or from 2014, it was 2.3 million barrels per day, and it's expected by 2030 it's going to be 5 million barrels per day. So after treatment, the oil sand, we will get the 10% bitumen, 5% water, and 85% sand. The bitumen is what is considered the heavy oil that's needed to be treated, which contains a high amount of hydrocarbons. The hydrocarbons are represented in cyclic compounds, also paraffins and heavy olefins. And that we're going to talk about in the next slides. Oil sand upgrading system, a little bit background about it. In general, it's divided into 3 main steps. The first one is the extraction and washing. The second one is the hydrogen to carbon ratio improvements, and then the hydrotreatment. And I'm going to touch upon them in a brief. The first one is the oil sand is actually, or the bitumen is recovered from the oil sand. And then the bitumen will be fed to the hydrogen and hydrogen to carbon ratio improvement to increase the hydrogen hydrogen rate for the bitumen. After that, it goes to the hydrotreatment, where the unwanted contaminants like sulfur and oxygen and even nitrogen is removed. And then after that, it's going to be the sweet crude oil. In between is that what brings us to talk about in my research. It's the main topic for my research. So I'll go deeper and deeper now for the next slide. So we said that the bitumen is actually fed to the fluid cooker. What comes out of the fluid cooker is actually in our particular interest, which is the naphtha. Naphtha is consisting of 20% of olefin and 4.4% of diolefin. When it goes to the naphtha hydrotreater, what's happening there is that we do have a catalyst called nickel molybdenum sulfide catalyst supported on gamma alumina. And this catalyst is actually tried to hydrogenate the naphtha or olefin and diolefin. By the end of the process, what happens is that some of the dimers dimerizes, and what happens is the catalyst deactivate and then the reactor shut down. To summarize this, I will talk about it this way. The conjugated olefin that we talked about, that's coming from, the conjugated olefin is actually 28% of olefin and 4.48% of diolefin. At the beginning, there will be a hydrogenation process that's happening on the NEMOS catalyst, or the nickel molybdenum sulfide catalyst. And then, at some point, at the end of the process, what is happening is some of those olefins actually dimerizes on the active sites, goes to the gum formation, and this gum formation will be dehydrogenated to form the coke formation, and that leads to rapid increase in the pressure drop and early shutdown for the reactor. So this is the problematics. We don't want to have our reactor shut down, the catalyst deactivation. From the literature, the hypothesis and speculation says that the acidity is coming from the catalyst, but from this type of catalyst. But where exactly it's coming from, and why the reasons happening is still unclear, and that's what we want to talk about in my research. So the study objective is to determine the effect of the catalyst acidity on the yield of diolefin dimerization over NEMOS catalyst, which means we want to see if there is a problem in this acidity, and there is a problem in the catalyst that because of the acidity where the dimerization is happening and the catalyst deactivate. And then we want to find the source of the catalyst acidity that causes the deactivation. And is it coming actually from the nickel molybdenum sulfide catalyst, or from the support, or this combination of both? And if there is any way to kill these acid sites to improve the activity of the catalyst. The research methodology. As for the research methodology, we do have the catalyst preparation. What we have done is that we loaded the nickel molybdenum sulfide catalyst on a different support that varies in their silica alumina ratio from 0 to 100%. And we tested for the hydrogenation dimerization of 4-methylstyrene, and we'll talk about the model compound in a bit. The second one, we took away the nickel molybdenum catalyst, and we used only the supports. Only the support, to see the effect of the only support in the hydrogenation dimerization reaction. The last thing is that we added NaOH base to kill the acid site and see if it makes any improvement for the catalyst activity. So as for the characterization, we use the ammonia temperature program desorption, which is used for the catalyst acidity measurement. And then the high resolution TAM for the dispersion. Lastly, the BET or into desorption, which is used for the textural properties of the catalyst. The assessment we took 8.4 weight percent 4-methylstyrene as a model compound found in naphtha at the certain relevant temperature and conditions from the industry, which is 200 degrees Celsius, 3.4 megapascal pressure at LHSV, liquid hourly space velocity 4, time on stream was 3 days. The experimental setup, so for the experimental setup, this is what we had in the lab, is that the following. So we do have the liquid tank where the feed is actually fed from there, and then we have the hydrogen is coming from the hydrogen cylinder. They meet inside the reactor, trickle bed reactor, and this trickle bed reactor where we have 3 phases. The liquid phase is coming from the feed, the gas phase is from the hydrogen, and the solid phase, which is the catalyst, where the reaction takes place. What's coming out from there is actually the products. So the products are taken from there to condensate in the condenser, and then for further treatment or further analysis using the GC-MS, gas chromatography mass spectrum. Here we want to talk about the acidity measurement that we said that we use the ammonia TBD. Here there is acidity change because of the support composition. We said that support composition from 100 silica to 100 alumina to 0 silica, and also because of the addition of NEMOS, which is addition of the nickel molybdenum sulfide catalyst. We can see that the catalyst, the peak for the acidity was around NEMOS over S10, S20 catalysts. The S10 means 10 weight percent of silica and 90% weight percent of alumina. Okay? So for the high resolution TEM here, we have the 2 images shows that the dispersion is actually, for the 2 catalysts, is not actually making that big difference. As you can see the numbers here. So mainly we can take out from this slide is that we have the only factor that plays a role in our study is the acidity, not the dispersion. We studied the a model compound using the 4-methylstyrene. That's coming out from it is the hydrogenated product and dimerized products, and we can see here from the second figure is that the acidity peaks where the dimers peaks. So for sub-conclusion, we can say that the dispersion of MOS2 is not actually impacted by the support composition. So that means the dispersion is not actually play a role. And then the acidity increases, we have the oligomerization or dimerization rate increases. We tested for the only support, as I said, because we want to see the difference. And when we use it, we found that after sulfiding support, we found that the supports has the same, more or less the same acidity, except for what? The S40 and SiO2. We use the same catalyst and the same condition and the same reaction. And what we come up with is that the acidity with the acidity with the dimerization is not actually changing for the 4 type of the catalyst, except for the S40 and SiO2 sulfide catalyst. Here is the comparison. If we can see, that's only at 1 weight percent, at 1 millimole gram of acidity. We have only 4 weight percent of dimers, and when we gone to the sulfide or supported catalyst, we got around 10 weight percent. So that's the difference between both of them. So that tells us the following, that the support acidity contributes around 40%, which means the acidity coming out from the support is only 40%. And the rest is coming from where? From the NEMOS catalyst. And there is something called synergistic effect reaction between the support and NEMOS causes this issue. The catalyst stability, so we want to do the comparison between the NEMOS catalyst over the support and the support itself. So what happened is that during the 3 days time on stream, the NEMOS catalyst over the S40 is more or less constant, the conversion, and then for the S40, which is the only catalyst, we see the decline happening. And why is that decline happening here? Is that we don't have more active sites to hydrogenate the 4-methylstyrene. Lastly, is like what we want to hear is that we took one of the highest acidic or most acidic catalyst, which is NEMOS catalyst, and we doped it with 3 weight percent of NaOH And we wanted to see if we kill this acid site, do we have an increase in the hydrogenation and diminishing the dimerization or no? So for the conversion, the one on the left, we don't see any changes, but for the right figure, we can see that the dimerization yield is actually shrink to almost 50%, which means that killing the acid sites increases the chance of, or the activity of our catalyst. The conclusion for my work here is that dispersion actually of metal is not actually impacted by the support composition. The support, as we explained, that contribute around 40% of dimerization yield. The NEMOS catalyst here shows a better hydrogenation stability compared to support alone. And we said why, because we do have more active sites that can hydrogenate the 4-methylstyrene. Dimerization yield is stable in both support and NEMOS catalyst. And lastly is the controlling the acidity using NaOH showed a promising result as we've seen in the previous slides, where we had the catalyst activity increased. Here is some papers that we published also with Dr. Hamad Mohammadi. And here is the acknowledgement. And thank you all for your listening. Appreciate it. Thank you.
شكرا دكتور. رحبوا معي بالمحدث الرابع لهذا اليوم الدكتور محمد يعقوب الخليل، المستشار في الشركة الكيميائية السعودية بعنوان تقييم الدي دي اي. تفضل دكتور.
السلام عليكم ورحمة الله. بسم الله الصلاة والسلام على رسول الله. رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي. First, I want to thank Saudi Engineering Council give me this chance to share my experience about evaluation of diethyl ether as renewable transport fuel. Nowadays, any country have committed to reduce greenhouse gas emission. Therefore, there is a need to introduce alternative fuel such as diethyl ether with less particular and greenhouse gas emission. What is the diethyl ether? Diethyl ether is oxygenated fuel with reasonable oxygen content, 21% and 64% hydrogen content. Benefit of diethyl ether. Affordable, can be obtained from conventional fuel and renewable source. Environmental friendly, very low exhaust emission, high energy efficiency, and available. What is the feedstock to produce diethyl ether? There are many types available and easy and simple to produce diethyl ether. Everyone considered diethyl ether only used in lab, but nowadays many countries have commercial mass production of diethyl ether. It can be produced from coal through coal to gas to produce syngas and ethanol. The main feedstock, all the main raw material to produce diethyl ether is ethanol. 2 molecules of ethanol produce 1 molecule of diethyl ether with the presence of sulfuric acid catalyst. Also, it can be produced from partial oxidation of biomass or from natural gas or crude oil, or from waste as we seen in the first session. Therefore, there is many easy sources to produce this type of fuel. Diethyl ether offer very good and better fuel properties in compared to diesel oil. It have a higher cetane number, low carbon content, high oxygen content, low density, low flash point, reasonable heating value. This study for fuel properties and the effect of addition of diethyl ether to diesel fuel has been conducted in the Khartoum Refinery Central Lab to show what the benefit of addition of diethyl ether to diesel fuel. Different blend percentage has been used according to distillation curve study. As we know, diethyl ether is more volatile, so it needs to be as a safety point of view to select the reasonable percentage of blend. Therefore, 5% and 10%, 15% and 20% have been selected to conduct this study. Once the density of diethyl ether is less than the density of the diesel fuel, therefore, the density of blend will increase inversely with the increase of the fuel blend percent. Also for the kinematic viscosity of the diethyl ether is less than the kinematic viscosity of the pure diesel. So, increase of blend percent lead to decrease in the kinematic viscosity, and this improve diesel fuel physical properties. Once diethyl ether have very high cetane content, so the increase of the blend percent improve the cetane index in the pure diesel. Also, addition of diethyl ether to pure diesel improves the engine performance. Single cylinder 4-stroke diesel engine was used to conduct this study at University of Kerry. And the result shows that the thermal efficiency will increase proportionally with the increase of the load, because we are using constant speed, variable load engine test. 10% blends shows that better improve in the thermal efficiency. Also, we have conducted different engine performance, such as fuel consumption. Fuel consumption also will improve when we increase the blend percentage. And direct thermal efficiency will improve when we increase the fuel performance, the percentage in the diesel fuel. Also, addition of diethyl ether to diesel fuel promise reduction in greenhouse gas emission, and this is enhanced many countries' vision and mission and commitment to reduce the climate change gases. Also, we showed from these figures, when we increase the percent, we can obtain less carbon monoxide emission. Also for NOx emission, at low density, we can see that we have reasonable reduction in NOx gas emission. But at high load, there is no significant change. In the conclusion, diethyl ether seems to be very attractive as alternative transport fuel that can be used in diesel engine up to 10% without major modification. Nowadays in Japan, Japanese use dimethyl ether in the transport truck. Diethyl ether has the potential to substantially cut down greenhouse emission. And also, it is non-corrosive to metal and does not require special material for structure and component of fuel system. We can use the existing structure. There is no need to study the effect. There is a need to study the effect of addition of diethyl ether in diesel price worldwide. Thank you.
نشكر الدكتور على المحاضرة الجميلة. أعتقد الآن وقت متاح للأسئلة، إذا أحد الحضور عنده أي سؤال أو استفسار بحكم المحاضرات اللي سمعتوها. تفضل. في مايك يا شيخ.
السلام عليكم ورحمة الله وبركاته. زيد بن عبد الحميد الحليبي، أستاذ مساعد في كلية الهندسة وجامعة الملك فيصل، مستشار مدينة الملك سلمان للطاقة. السؤال للدكتور الحميدي مشكور، ذكر أن السيلينج برايس 0.6 $US بير جلون. كم السعر في السوق اليوم؟ إذا كان هو السيلينج برايس، أنا اللي فهمت أنه هو الآن الكوست بيس على الستدي اللي أنتم عملتوها. كم البروبوز سيلينج برايس حقيقي اليوم؟ وكم الماركت اليوم ينباع؟
الله يعطيك العافية. مدري الصوت واضح؟ الله يعطيك العافية على السؤال. سؤالك يقول السيلينج برايس كم الآن بالسوق؟ صحيح. الآن بالسعودية الجالون تقريبا ريالين وقول 50 هللة يعني مع الكوست حقته. احنا عندنا 60 سنت بير جالون، الجالون 3.72، يعني بيطلع لك تقريبا شيء و5، يعني انت طالع يعني بربح تقريبا دبل. يعني اذا حولته لل as a fuel. But there is another concept على producing the fuel. How about recycling? If you compare between recycling and producing hydrocarbon fuel. يعني الحين في بعضكم يقول طيب اوكي خلاص بلاش ننتج بلاستيك، خلينا كله نحوله converting to fuel.
صحيح.
Reducing the plastic is make more profit than converting to the. If you recycle it, is better. And also, we conduct another study is going to be published about comparing the recycling and plastic compared to the reducing the hydrocarbon fuel from the plastic. But the initial result is showing the recycling is better. The cost of production تقريبا for plant capacity 1,000 dry metric ton per day. Yearly it costs around 27 million operation cost. Does that answer your questions?
Yes, very clear. Thank
Okay,
you
الله
very
يعطيك
much.
العافية.
السلام عليكم زميلكم الدكتور عبد الرحمن المذن رئيس قسم الهندسة الكيميائية بجامعة الملك فيصل. Thank you everyone for your great talks. My first question is directed to Dr. Arshad. Have you done any comparison to pure platinum supported on alumina? Because I've seen comparison with platinum with other promoters. The other part is what is the nature of those promoters? Are they in the form of a single atom catalyst or something else? If you have any idea.
I beg your pardon. I just understand the first part of the question. And the first part of the question probably is that, do we have a study where we studied only with the pure platinum, right?
Yes, supported on alumina.
Supported on alumina. We didn't conduct that study because it is a very well-established phenomena that platinum itself is a very, very expensive metal. So we do not want to use that much expensive catalyst. So what we did, we want to have a better dispersion of the required stoichiometric amount of platinum, which can be supported very well on a highly porous materials. So based on the literature and based on the past studies, we prefer to take that study as a precedent and build up on that. That is why we did not conduct it. Yes, we conducted platinum and tin on gamma alumina. And we figured out that the certain ratios of platinum and tin has a significant impact on the dispersion of the platinum. And I hope I have answered the first part of the question. I couldn't get the second part.
Yes, I see your point. But the second part is about the nature of the promoters.
Okay.
Are they in the form of a single atom catalyst, or what is exactly the nature? I know that you haven't done any characterization, if I'm not mistaken. Right?
We did some characterization, and the moment, due to some classified information, I cannot reveal that. And based on this, if you say that, in general, I can tell you that the promoters, what we studied, has a different role. For example, if you add zinc, it enhances the dispersion of platinum to the tin. And if we add calcium, it reduces the surface acidity of the sport. And if you add indium, what happened there? The indium, in the presence of a certain proportionate of hydrogenation ratio, enhance the dispersion and attract the absorption and physioadsorption and chemioabsorption of our N-butane to the sport itself. And there was a phenomena where we face a bit tricky approach that there is a more coking formation. So we are blocking our active sites. So what we did, we tried to reduce the active number of platinum, and this study is still in the pipeline. I hope so. Inshallah, we'll be able to share a good result with this audience.
Thank you so much. The other part is directed to Dr. Majid about the nickel molybdenum sulfide and the nature of the acid side. I would expect that based on previous studies, we have done previous studies on nickel phosphide, and we were also wondering about the nature of active site, whether it is acidic or not. And we have done electronic study on nickel phosphide, and we have seen a small charge transfer from the nickel metal to the phosphorus atoms. So this is probably also what is happening. I'm not sure, but this is maybe my guess about the nature of the acidic side on molybdenum or nickel molybdenum sulfide. Maybe there is a charge transfer from the metal to the sulfur atom. So if you could elaborate on this.
Sure. Thank you. It's a very good question. Actually, I'm having slides about that, but for the sake of time, I couldn't really explain that in depth. We do have the charge transfer between the nickel molybdenum itself, which is the metal, and also between the nickel molybdenum, between the support, silica and alumina, both of them. And we have done the test for the type of the acidity, which is Lewis acid sites and pronicid acid sites. What we come up with is that we do have the more or less the same correlation when it comes to the total acidity, which means that the Lewis acid site and the pronicid acid site are all combined having more or less the same effects when it comes to the acidity, the reason of the acidity. Because when I read, you're right, when I read it in the literature, that some of them said that maybe the promoter is the reason for it. Some of the others said that maybe the MOS2 with the hydrogen is the reason. So I have done distinctive study about it using the IR pyridine to distinguish exactly what is happening. And I came up with the results that nickel and molybdenum, the Lewis acid site and pronicid acid site more or less having the same exact effect on the on the acidity of these type of catalysts.
Thank you so much.
شكرا للجميع. نظرا لتأخر الوقت اسمحوا لي أرحب بالمهندس يار رجاني عضو مجلس إدارة هيئة السعودية للمهندسين لتكريم المتحدثين، فليتفضل مشكورا. نذكر الأخوان الحضور أن الساعة الواحدة سنبدأ السيشن الثاني إن شاء الله.
Yes.
اسمها مايكرو ستارت، شركه حقيقه. في وقت اعطيه ستارت.
لا موجودين كلهم. اي بسم الله. إيه. اوكي خلاص. نعم. بسم الله. بسم الله الرحمن الرحيم. باسم الهيئة السعودية للمهندسين وشعبة الهندسة الكيميائية نرحب بكم في الجلسة الثانية والتي عنونوا لها المنظمين المواد المتقدمة. اسمحوا لي في البداية أن أرحب بالضيوف الكرام وأرحب بالمتحدثين. سيكون معنا الدكتور سيتا رامولا من جامعة الملك عبد العزيز، والمتحدث الثاني الدكتور سعود الصاعدي من جامعة الملك عبد العزيز أيضا، والدكتور هيثم حديدي سيكون المتحدث الثالث، وأيضا معنا المهندس محمد عثمان من جامعة الملك عبد العزيز. ستكون أول محاضرة للدكتور سيتا رامولا بعنوان إنتاج الهيدروجين بواسطة تحلل الأمونيا باستخدام محفزات الكوبالت المدعمة بخليط CaCe. فليتفضل مشكورا دكتور. تفضل. ننوه أن 15 minutes for each presenter.
Yeah, good afternoon all of you. Thank you for giving opportunity. So my name is Sita Ramulupadila. I am from the King Abdulaziz University. Okay, so here is my title, Hydrogen Production from Ammonia Decomposition by using cobalt catalyst supported on calcium cerium mixed oxides. And we studied the ratio between calcium and ceria. Okay, so these are my headlines of my presentation. So it's some introduction part. I will show you some introduction part, and just a small literature review and my objective, and we will follow by research methodology, what means how we choose the catalyst, and then we will discuss the result and discussion, and finally conclusion. Okay. Yeah, before starting the introduction, I think all of you guys nowadays come across with the hydrogen energies. In every website and everywhere you are finding this, right? So that means the whole world is turning towards the hydrogen, because to avoid the carbon monoxide and carbon dioxide, which are major greenhouse gases effective influences. Okay, so the hydrogen. So hydrogen is considered the best unconventional fuel. So you can see that. So here there are recently the Toyota and released the Toyota Mirai fuel cell car, and even Honda also, Nexon, and even Volkswagen also they released a hydrogen car. And also they are also running the trains and ship, and there are a lot of things. Okay, so here so now the future is completely depends on the hydrogen. So hydrogen is why? Hydrogen is because hydrogen is a best unconventional fuel. It is a clean power and more efficient than another source of energy, and versatile. It is versatile fuel we can use in any sector, automobile, industries, and everywhere. Okay, so what are the difficulties with this one? So using hydrogen is okay. So there are some difficulties, major difficulties. What is that? So it is unsafe to transportation. We cannot transport hydrogen as easily, because as we know, hydrogen is highly flammable, right? So, and also it is the cost of liquefaction. If you want to do storage, you have to make it in a liquid form. You cannot put it in the gas form. So we have to make it in the liquid form. So for the storage, for the making of liquidation, so it is needed very, very high costly. Okay. So here for that, then what is the alternative way? So that is the alternative way. We need some hydrogen carrier. So that we can carry the hydrogen so safely with low costly, and then whenever we want, we can take out the hydrogen. So and that one, so there are a lot of hydrogen carriers are there. Among them, the best one is ammonia is the best energy carrier. Why? So ammonia it has the advantage, high energy density and high hydrogen storage capacity, and it is mainly thing is COX-free hydrogen carrier, and ammonia can be liquefied at low pressure. It is around 8 bar or 10 bar, 8 to 10 bar between 1 atmosphere pressure, so 8 to 10 bar pressure and at a room temperature. Okay, and it is inexpensive fuel and available in large quantities. Why? Because already the ammonia production technology is established all over the world. Haber was processed and the infrastructure also available. The tankers are available, the transportation is available. Everything is in our hand. So we can use the ammonia wherever we wanted to transport it, we can use it and we can store the ammonia as easily compared to that of hydrogen. And ammonia, so from ammonia to produce hydrogen is a single step reaction. And there are other hydrogen carriers are there, but they will use the multiple steps. So for example, methane and methanol, there are others are there, but it will give the multiple steps. There we will get hydrogen in multiple stages, but there we will get at the same time, we will get the carbon dioxide and carbon monoxide. But here, the ammonia is a single step reaction. That means we will get 100% selectivity. Only we have to focus on the conversion. Okay? So now, I will just, because in most of the cases everywhere I presented some of the results. So they will ask that, okay, you are producing ammonia from hydrogen only. Again, you are taking from the hydrogen from the ammonia. This is a basic question which is all that encountered from the many people. yes, of course, hydrogen so is producing from the fuel, and then where we are converting it. Here the question is how to transport the hydrogen. So we are using ammonia as a carrier. Okay, I will give next slide because what is the cost effective. So you can see there are two properties. So ammonia is having the gravimetric density is 17.8 and volumetric energy, hydrogen density is more than the pure hydrogen. And the cost, if we come to the cost, the production cost for the ammonia, it is $3.8 per kilogram of hydrogen. Okay? And for the taking from the fuel, the hydrogen cost is around $3 per kilogram of hydrogen. And for the transportation cost, if I take 1,600 kilometers, the transportation cost is $0.19 per kilogram of hydrogen. And whereas if you use the pure hydrogen, okay, the transportation cost is started from the $0.51 to up to the 3.2. It is more than 30 times. If you just see that. So, and storage cost capacity, if I wanted to storage the hydrogen, okay, for the 15 days, it is, if I want to storage ammonia, it's $0.06 per kilogram, okay? But whereas hydrogen, it is 1.97. It is 30 times far than, right? And if I wanted to store ammonia as 182 days, it is around, so $0.54 per kilogram of hydrogen. But whereas hydrogen, it is $14. 14 is far by the difference, okay? And the supply cost is for the ammonia $4.4 to $4.5 per kilogram of hydrogen, and whereas hydrogen is 5.5 to up to 21. It is reaching up to 21. It depends on from the sphere, the storage cost and supply cost, all including it reached up to 21. So these are the production. However, if you see all over the cost wise, so ammonia is the best energy carrier, hydrogen carrier compared to the hydrogen, pure hydrogen. Okay, what we will do? How we will do? So here is the answer. Here we will transfer the ammonia and the trucks or shipment wherever we want. We can take, and then we will store, and whenever we want the hydrogen, we will decompose the ammonia and converting into the hydrogen. So here is the reactor. We will place the catalyst. So here the catalyst, and the catalyst will decompose the ammonia into nitrogen and hydrogen. Okay, and if there is some small amount of nitrogen in ppm level is available, that can be purified by putting some ammonia absorbing materials. It's already available. That means I can release the hydrogen from the ammonia less than 0.1 ppm level. That much purity of hydrogen we can produce, okay? So here, once you hydrogen produce, you can put it in the fuel cell vehicle, car, wherever we want, and then we can use it, okay? So here, the catalyst for the ammonia decomposition, generally ruthenium, nickel, and cobalt-based catalysts are using, okay? Next, we will go to some literature review. Okay, here, up to the till research studies, the many catalysts are studied about the ammonia decomposition, but among them, the ruthenium is the best active metal for the ammonia decomposition. But so ruthenium, we know that the ruthenium is expensive metal. We can't put all over the world the ruthenium. It is not available. To be frankly, it's not available. So we don't have that. The ruthenium we can use for the high scale. Okay. So for what then? So we will go to the other option is we have to look for prepare a catalyst for iron, cobalt, or nickel. So we have to go to either of these three, okay, because these are easily available, and compared to the ruthenium, is cost-wise also is very less, okay. And then this is the active material, and then we can disperse. We cannot take all the bulk metals for the reaction, so we can disperse on the support, and support also very important. And so there are many supports they are tested for the ammonia decomposition. Among them, so carbon nanotubes are the best showed on ruthenium. They showed the best activity. But here again, the carbon nanotubes is also a problem, because when you do the ammonia decomposition, hydrogen will form, and then the hydrogen in the presence of ruthenium or in the presence of cobalt and iron, again carbon nanotubes will react, and again it forms the methane. So there is a problem, methanation problem will be there on carbon nanotubes. So, and also the metal agglomeration is high on carbon nanotubes. So then we have to select as another alternative support. Okay. So now this is our objective. So we have to develop some material which should be highly active for ammonia decomposition reaction, and we have to investigate the catalyst effect on the reaction operating temperature. Okay. So what is the material? So we selected here some mixed oxide, calcium and cerium. Why we selected this is the calcium and cerium? So there are two reasons. One, I would like to say this cerium, this fellow is having a very good property. What is that property? Whenever it is interact with the metal, so because it contains oxygen deficiency sites, so it will, whenever it is interact with the metal, it will increase the metal reducibility, because finally when you perform the reaction, the metal should be in the metallic form, metal not in the metal oxide form. So when you do the reduction, so the metal reducibility is increased by the cerium. And what about the calcium? Calcium will give the basicity of a catalyst to increase the basicity. This is also one of the important property for ammonia decomposition reaction. So that's why we choose the calcium and cerium. So we mixed both mixed oxide. And then we prepared the support material here with different ratios of calcium and cerium with 1:1, 2:1, and 3:1. Here, these are the supports, only support, no active metal. Only support material we prepared with the different ratios by changing the calcium ratio. And then after preparing the support, then we added the nominal active metal, 5% cobalt. Okay, we choose the 5% cobalt. So, okay, and then on all the same support. Then we tested these catalysts for ammonia decomposition reaction, how this ratio are influencing on the reaction. Okay, let's go and start the resultant discussion. Okay, first I would like to check what is the textural properties of a catalyst which I prepared. Here you see in A and B graphs. In A graph, only pure supports which I prepared with 1:1, 2:1, and 3:1 by changing the calcium as the amount with 1, 2, and 3. Okay, and later the B part I added the active metal cobalt. Okay, first you see in the A graph. So by changing the amount of the calcium, you can see that the curves is changed, which means there is a change in the pores. Okay, so the surface area also will change by increasing the calcium. Okay, so here you see the red one is a 1:1, and the blue one is a 2:1, and 3:1 is the green one. Okay, then another important information I found from here. What is that? After adding the cobalt, have you seen any changes A and B? No, I'm not sure. I'm seeing clearly there is no change in the catalyst. That means the support is allowing the active metal without any changing, right? So that means that is also very important thing which we need for the reaction. If support, after adding the metal, if support is itself is changing the structure, then everything will lose. So I want a support should be same like that, same properties, so same textural properties after adding active metal also. So that is the active metal is, so these supports are allowing the active metal without any change in the structural properties. Next we will see the pore size distribution also. You see this is by changing, only 3 minutes? Oh, it's too much, okay. I'll quickly give it just 5 minutes. Okay, so these are, see, here also the pore size distributions. So there is no change after adding the cobalt, okay? So, but with increasing the calcium amount, there is a change. If I give the values, you can see there is a surface area value after 1:1, 2:1, and after 3:1, there is decreasing. But after addition of cobalt, in the 1:1, there is a drastically 110 to 76. But in the 2:1, 76 to 70. And in 3:1, 71 to 42. So the difference, only 2:1 ratio is showing very less, okay? But which means that ratio is optimal, okay? In XRD results also, you see here, XRD results also is showing no change in after the addition of the cobalt, okay? Next one is the TPR studies. If you see the TPR study, this is a very important study here. So we put this temperature program reduction studies, and 1:1, the red color one is not reducing. That means there is a strong interaction of cobalt, calcium, and cerium, which is not at all reducing at all. Okay, at a given temperature up to 800, if I heat the catalyst under hydrogen also, there is no reduction in the cobalt. But in 2:1, that is increasing, and 3:1 is still highly increasing. What is happening in this one? So there is 3 important properties. So here in 1:1 ratio, the cobalt is interacting with the calcium and cerium. The calcium is interacting with the cerium, and the cobalt is interacting in the calcium. Okay, in 2:1, the cobalt is interacting in both simultaneously. I will show you in the next slides. And in the 3:1, the cobalt is interacting with the cerium, not than the calcium. How can you say that? You may get the doubt. How you can say that one? I will show you in the next characterization. But before that, you can see, so the reduction consumption value here, the support is giving in 2:1 is 140, the calcium, and after adding the cobalt, the value of the hydrogen consumption is 311.21, and the 2:1 ratio. Okay. So next, if I go to the basicity also. Basicity also is important property, as I told you. So in 2:1 ratio, the basicity is increased compared to the 3:1 and 1:1. Okay. Yeah, just finished. These are the morphological studies. Okay, you see this is morphological studies after the addition, there is agglomeration is happening in 3:1. Okay, and 2:1 is there's a particle sizes are really okay. Then we perform the elemental mapping, which is very, very here interestingly. You see here in the elemental mapping, all the colors of red, green and blue. So here in the first one case, it is dispersed clearly on the calcium, and under that one cerium is there. So that's why they are interacted very strongly. So which I show in the previous slide in TPR is not reducing. But whereas in the 3:1 case, if you see that one, the particle, the cobalt in blue color is interacting with the red color one, which is cerium, not with the calcium. So we can clearly seeing that one here in that picture. But whereas come to the calcium cerium 2:1 ratio, so the cobalt is dispersing equally with the calcium and cerium simultaneously. That's why we are getting the properties in that direction. So we just now presented. What about the activities? So if you see the activity, so in the 2:1, you see that the ammonia conversion, because 100% selectivity is there, the ammonia conversion at 550, it's 96% I'm getting, and 575, because I didn't mention that the 575 temperature, at 575 I'm getting 100%. But whereas the other catalyst ratios are low. Okay, so these are the activity results. Next, if I go to the Arrhenius plots, if you even see the activation energy for the 2:1 is very low. That means that the catalyst is very highly active. Then, so I selected the calcium cerium ratio 2:1. Then we optimized the cobalt loading, because previously we just take the nominal loading of 58%. Then we increase the loading and we see up to which is the optimum loading of cobalt. Then we see 10% cobalt loading is giving almost at 550 degrees, 99%, 98% of the conversion and with 100% selectivity. So this is the condition. Then we also tested the catalyst stability. The catalyst is stable for a long time. We tested for 70 hours with high GHS, varying the GHSVs also, space velocities also. You see the 6,000 GHSV, 12,000 and 30,000 GHSV also. The catalyst is stably giving the activity. Okay, so these are my conclusions. The results concluded that the calcium cerium mixed oxide is a promising support for ammonia decomposition reaction, and the ratio for calcium cerium ratio is greatly influencing the catalyst activity, and calcium cerium ratio is equal to 2 is the optimal ratio for ammonia decomposition, because it has a high basicity and suitable metal support interaction and easily reducing the cobalt species. And the 10% cobalt loading is suitable for the calcium cerium 2:1 for support, okay, for higher activity. And we studied this catalyst is stable for the time on study. We studied for 70 hours period of time and very active, okay, and we even at high space velocities. Okay, I would like to thank you, my university and the DSR, which is funded for this project. I finished this project and I just published in Journal of Rare Earth Elements recently. I didn't get, it's not for coming on the online, but it's accepted. Okay, so thank you for all for giving this opportunity.
ثانك يو دكتور. رحبوا معي بالمتحدث الثاني الدكتور سعود الصاعدي، الباحث الدكتوراه في جامعة الملك عبد العزيز بجدة كلية الهندسة. تفضل مشكورا، بعنوان جهاز المستشعرات الموانع الدقيقة المرئية.
Assalamu alaikum wa rahmatullah. Hi everyone. I am Saud Al-Saadi. Actually, I'm not a professor right now, but I am a PhD candidate, but that's optimistic news for the near future, inshallah. I want to get the chance to thank and congratulate the Saudi Council of Engineering to have this successful occasion, and I'm blessed to be involved to participate in this conference. I'm going to talk about flexible microfluidic device with non-planar interdigit microelectrode. Here the agenda. Introduction, I will give you materials, methods for fabrication and electrochemical impedance signature and future direction and the conclusion. First of all, we try to manufacture flexible, stretchable, wearable, and durable non-planar interdigit microelectrode to detect emerging contaminant like bio threat or chemical threat or even radiation threat. We also made non-planar interdigit microelectrode made from non-flexible device, and our first question: why do we need the sensor? Next generation of technology such as AI application and Internet of Things depend on the sensor. Also, the health sector need rapid detection for disease because, for example, the cancer can't be detected until the advanced stages. So by using the sensor, we can detect the cancer or disease or chemical threat in early stage. This schematic shows the development cycle sensor. We start with the material selection. We made our design. And we made to measure the analysis, sensitivity and selectivity, make analysis methods, then we make a cost estimation. So by this cycle, we can get the optimum sensor development. Also, this figure can simplify the concept of microfluidic device. We have analyte and transducer materials, detect the analyte and give signals to digital modification and analysis method. Also, this is the chart shows the concept, the same concept. And the second question, why do we need a flexible device? Flexible microfluidic device. A flexible microfluidic device cover large area of chemistry, biology, rheology, and electronics application. A flexible microfluidic device have more advantages over the conventional electrodes because we can control the valving and bumping and mixing. Also, we can control the cross-sectional channels. Also, can we integrate it with different systems, like impedance system, and the possibility for 3D printing of a microfluidic device. Finally, it's unbreakable and unharmful to involved in tissue, human tissue. For detect, for example, some enzymes like dopamine or whatever. After that, thereby, we come up with a novel device architecture with using bucket flexible, transparent top and bottom layers integrated with non-planar interdigited microelectrode. Our device, by using this 3D electrodes, we increased the sensitivity and selectivity. And because we used backed materials, we have good mixing, and we bring the concept or phenomenon of a backed bed reactor to this kind of device. So we have high efficiency mixing. And that's a solution over the conventional planar interdigital sensor. This is process flow diagram. Summarize the methods of fabrication, flexible electrode. And this is a lithography protocol for flexible non-planar interdigital microelectrode. We started with material selection, clean the substrate, coating, soft baking, and using a mask aligner, using UVE. And there is a new and advanced technique used for right now in this technology, like optical correction using extreme UV. After that, we developed our electrodes, then followed by deposition and etching our left of the over material. Starting with choosing the BET, we have used different materials. Here we can give two examples of two substrates like BDMS, polydimethylsiloxane, or polyethylene terephthalate. We make a comparison between some properties, melting temperature, modulus, tensile, and we choose, for example, started with using BET. Here we made our mask using software or coding, and there is two kinds of mask, channel mask and electrode mask. This is a figure summarize the concept of lithography or metal deposition using E-beam or pulsed laser absorption, deposition. And this is a lithography protocol This figure summarizes the concept of starting from coating and using a mask and develop the electrodes and metal deposition. Actually, we used different kinds of materials to make our electrodes, like platinum, gold, or chromium. This is figure shows the microelectrodes under a microscope, and here is the scale in micro scale with a length of 10 micron and width of 100 nanometer and a distance in between 4 micron. We come up with new methods for assembly our device using a microscope to align the top and bottom device layer over each other and fill it with nanoparticles. We used here, for example, FAMIL 101, and the average grain size is 160 nanometer. And we can fill and back our device with different materials like metal oxide framework. And we already published a paper about using this kind of material to detect PFAS. Finally, we come up with this flexible device, scratching from the surface and raw materials. We come up with this flexible device, detect even below 1 nanogram. Then we make a characterization for equivalent for our device to get equivalent circuit for the device. For example, we used AIS, impedance electroscopy. We can use also cyclovoltammetry. After acquisition data, we fit our device equivalent data to get the equivalent circuit device. For example, here we used Z-symbol software. Finally, the future direction and conclusion. We have a novel design flexible microfluidic non-planar integrated microelectrode. Material selection, fabrication, characterization, and analysis. The flexible device were studied and analyzed. The device is modular, adaptable, and upgradable. So we can use different materials and different analytes to detect. Future work include AI for data acquisition process. We try to apply the device in different embedded system application. Thank you.
شكرا مهندس سعود. المتحدث الثالث لهذه الجلسة الدكتور هيثم حديدي من جامعة جيزان كلية الهندسة بعنوان الورقة دراسة التغيير في التركيب المجهري والسلوك والأداء الميكانيكي لمادة الفولاذ. نذكر الأخوة المتحدثين أن المدة 15 دقيقة، سيكون إن شاء الله هناك وقت بعد البرزنتيشن للأسئلة والمناقشة.
السلام عليكم ورحمة الله. Good evening, everyone. Good afternoon. This is Haytham Hadidi from Jazan University. Today I'll be talking about the role of hybrid additive manufacturing in industrial and practical applications in mechanical and chemical practice. I would like first to thank the Saudi Engineering Council for the invitations today. I'll take you in a small trip. This small trip will give you an introduction about what is hybrid additive manufacturing, the meaning of hybrid and the meaning of hybrid additive manufacturing. And then we'll talk about the motive that drive us for this research. Back in 2017, there was a very huge demand for hybrid additive manufacturing for the lack of mechanical properties that are obtained from 3D printing, or what we call additive manufacturing. The reason behind this research was the need for high strength materials, but at the same time, lightweight structure. And this drives us to the idea of using or coupling additive manufacturing with another processing techniques. And that's what I will talk today about. So the main objective of this is to come up with some products, some tools that are capable to be implemented in mechanical and electrical environments without having a counterpart or without having conflicts in terms of performance. The aircraft and the aviation industry, automobiles, the army and the navy as well as the pipeline and the oil industry and refinery. This is what drives us as a group to go deeper into the term of hybrid additive manufacturing. So the current approach that most of the people are using right now is what they call the honeycomb approach or the composite approach, where they can manipulate the geometry of the parts to improve the performance. And using composite material is another approach that people are currently using. And the surface coating is a third approach that are actually currently being used for modifying the mechanical properties, chemical properties, and corrosion resistance as well. The limitation in these three techniques that most of people are using right now, there is a limitation in terms of material being implemented and used. Not only that, but also the complexity of parts. You cannot make a very complex geometry. And the damage inspection is another limitation. The cost is one of the major limitation in terms of using the composite materials and the honeycomb structure. The difficulty in manufacturing that has been overcome by the use of additive manufacturing, and that's why we propose the solutions of using hybrid additive manufacturing. So the desired outcome of this research was to achieve a solid, functionally gradient single materials, meaning we can produce a composite materials with a gradient, functionally gradient materials using just a single materials that is being implemented in the manufacturing process, and instead of having 2 different or 3 different materials at the same time. And that's what we have succeeded as a group in producing. The hybrid additive manufacturing, or the terminology that we usually use is hybrid AM. AM is an abbreviation for additive manufacturing or 3D printing. What is the advantage of using such technology? We can control what we call the local properties. The local properties is not only the surface property that is being produced when using a coating or honeycombs, but we can go deeper into the internal structure of materials. And that's what we call it local properties. Local meaning by global and local properties at the same time. So we have also another advantage, which is the freedom of design. Whatever complex part you have, we can produce. Not only that, but also that allows us to avoid the limitation of damage inspections, and also for some complex part that is very hard to make using conventional machining or conventional manufacturing processes. The third advantage, which is complexity for free, meaning by you can increase the complexity, the cost will marginally be increased, because most of the time what we do in the 3D printing world or additive manufacturing, you make the part as complex as possible, and that will not affect the process, because the complexity is coming from the design of the part that is just a minimal effort you can do using AutoCAD or SolidWorks. The machine itself will do the remaining job. So what is additive manufacturing? Today I'll be focusing on metal additive manufacturing. There are many different technology that is being used now, one of which is what we call directed energy deposition, or DED. Directed energy deposition is a terminology used where you have a powder spraying from a coaxial nozzles, and you have a laser coming from the middle of the parts. It can melt and solidifies the powder as it's being deposited into the parts. And then when we have the powder bit fusion, BBF, and also we have the sheet lamination as well. So what we mean by hybrid additive manufacturing or directed energy depositions, as you can see on the screen, you have a powder coming out from a coaxial nozzle, 4 coaxial nozzles or 3 coaxial nozzles, and then you have a high power laser. It can go up to 2 kilowatts. Coming from the metal, it can melt, deposit, and print the powder it's being deposited at the same time. So the term hybrid additive manufacturing is coming from the fact where you use one or more secondary processes or energy sources with 3D printing. The 3D printing terminology is a common now, where you use a printer. This printer is printing parts a layer upon layer. What we have done, and this has got patented a couple months ago, is you use 3D printing and you use a secondary processing at the same time, simultaneously. So you do printing and then you do processing in situ, inside the printing chamber. And then you print again and then you do the processing again. So as a result of that, what you do most of the time, as we just mentioned at the beginning, when you do surface treatments, the only affected region is the surface. As you can see in the left side picture, you can do the traditional modified surface integrity, and the only surface affected is the outer surface. And you can go deeper, probably about a 1 millimeter or 2 millimeter deep into the surface, where you have the properties of the microstructure changed. Now, using the hybrid additive manufacturing allow us to do what? To do a local integrity, meaning by, and instead of just affecting the outer surface, and I can do deeper microstructure evolution and changes. As I can print layer upon layers, I can change the microstructure as I'm printing from bottom to top. And that's what you can see in the right corner picture. You see the microstructure is going and refined along the surface and along the length of the sample that we printed. The picture on the right side, on the top right side, is an actual 3D printed sample that we have printed. What if we could print mechanical properties instead of measuring mechanical properties? That's the purpose of the 3D printing and hybrid additive manufacturing. So the objective was, okay, what I want to do, I want to do 3D printing, but at the same time, I would like to do a microstructure change as I print from layer to another layer to the third layer until the top of the samples. And that's where we have a synchronized two processes at the same time. On the right corner pictures, you see what we call lens. Lens is one technology that is a laser net engineering shaping process that is used laser as it being printed. And then what we do, we did an LP. LP is a laser peening process. It's one of the surface treatment processings that is being mostly widely used in the recent couple years. So what we do, we print using lens, and then we do laser peening, and then we print, and then you do laser peening. The material that we actually printed in this technology as a first trial was the 420 stainless steel. And the reason why we have used this, because of its availability and because its variation in terms of applications. So the local integrity will enable us to do micro and nanostructures that was not being available without having the hybrid additive manufacturings. The hardness as a local integrity can be improved not only in the upper or outer surface, but it can improve, as I will show later on the presentation. I can manage and I can control the hardness as I can go from bottom to top as well. And the wave speed characteristics is another benefits and advantages that I can use using the hybrid additive manufacturers. On the other side, what I would like to do as I change the global integrities or the microstructures, I would like to get some benefits from the mechanical behavior, not only mechanical behaviors, but also the corrosion behavior, the chemical behavior as well. So what if I can use it not only in a mechanical application, but I can use it in making the reactor for chemical application? What I can use it for electrochemical electrode. I can use it for blasting, which is blasting erosion arc machining processes. What I can use it also, I can use it in the field of combustion chamber. How can I make a combustion chamber that can sustain a very high temperature? Not only that, but I can find spalling from the high temperature inside there. I can also resist the pitting and the crevice corrosion as well. So the hybrid additive manufacturing and the methodology that we have followed. What we did actually is we brought what we call optomic lens hybrid additive manufacturing, and we implemented the technology here. So using a layer by layer and printing layers upon layers and then doing the laser peening enable us to what? Enable us to reach to this conclusion of the result. So instead of only affecting the outer surface of the part, I can go deeper now. On the left side, the microstructures of as printed. So what we did just printing process, 3D printing process for one of the samples, and then we measured the microstructure along the length of the sample. We have seen and concluded that there is a microstructure change and microstructure refinement as from the top to the bottom. But when we did the hybrid additive manufacturing, it was even more interesting. We have got to the points where we have a very refined microstructure. This refined microstructures will give us to the conclusion of that. When we went deeper into the nanoscale and the nanostructures, we have got to the conclusion, and the result indicated that there was a very huge amount of subgrains created from hybrid additive manufacturing. And these subgrains, when we compare it to just the 3D printed one, it was doubled. For example, and for instance, there was a very high dislocation density, and it was very high subgrain. The subgrain size in the as printed without having any hybrid additive manufacturing was 157 nanometer, the grain size. Meanwhile, in the hybrid additive manufacturing, the subgrain size was 109. It was probably about 30% reduction in terms of grain size. This 30% reduction enabled us to improve the properties 300 times. So what happened is that the density dislocation inside the parts, and instead of having 3 times 10 to the power 13 density dislocation by meter square, we have got the double, 6 times 10 to the power 13 over the millimeter square of the hybrid additive manufacturing. So what will help us in? When we did a hybrid additive manufacturing, we tried to map the hardness along the surface of the 3D printed part. It was very interesting is that we can actually control the hardness. We were able to manipulate the hardness, meaning instead of having just one hardness value for the parts, for the 3D printed parts, now we can print hardness. We can manipulate the hardness. We can control the hardness. The blue color here indicate that the hardness can be changed across the surface of the materials. Okay, if that is actually happening, what am I getting from these hardness change and microstructure change? We did mechanical properties, characteristics, and we did a quasi-static performance, and then we did high-strain performance, like a ballistic performance, when you have a bullet coming out from a gun and hitting an armor. And this got us a very interesting result. We were able to compare our result to the available market samples. The 420 steel that is available in the market, it was only 600 megapascal. We reach a value of triple, that is meaning by 1,800 megapascal in terms of modulus and in terms of high strength. That also led us to what if we are using these applications in a very corrosive environment, in terms of corrosion and in terms of chemical properties. And this is our next step. So what we want to do, because the 3D printed parts usually have an impurities in the outer surface, where we do 3D printing and we do hybrid additive manufacturing, and instead of having a residual stresses, these residual stresses is being wiped off with the heat generated. You see the picture here? It's like you are welding instead of printing. The high localized heat, it affecting the materials and it forming an oxide layer. This oxide layer will accelerate the corrosion behavior. How does the hybrid additive manufacturing help in this way? What we can do, we can print, and then we can do the machining while we're printing. And by doing so, we improve and we do a grain refinement. We improve the surface morphology and surface topography as well. But also, we are maintaining the residual stresses. You see here the blue curve and the red curve. The red curve, when you print, you actually print with residual stresses, compressive residual stresses. These compressive residual stresses will resist the corrosion behavior. But when you do printing again, you apply a very huge amount of heat. This very huge amount of heat will eliminate and wipe off some of your properties. When you do 3D printing and then you do laser peening, you again make another compressive residual stress cycle. These cycles are to be implemented for the sake of improving the mechanical properties. Now,
Doctor, if you can go fast, please.
the goal is, you see the picture here under residual stresses. There are two pictures. The goal is to maintain the compressive residual stresses. While maintaining the compressive residual stresses, the picture beside it, what I want to do, I want to have the compressive residual stresses in the negative region. The reason why I want it in the negative region is to resist the corrosion behavior. And that's what we are projecting. The picture below it is the residual stresses along a couple cycles. On the right side, we did a mapping for the microstructure and the grain. And this is what we are aiming to. In the corrosion behavior, as a future work, we are working now with a group in Purdue University and University in Nebraska, US, to do a corrosion characteristic and study. What we are projecting is the right picture. You see on the right side, what you want to do, you want to have the mass loss and the reduction in mass in terms of material is to be minimized as possible. That's why you maintain your corrosion. You don't want your material to be corroded very fast. And this is the corrosion analysis apparatus we're using. We're using the potentiostat, and the potentiostat, we're following two standards, the ASTM standard G48 and the 220. And by doing so, I'm ending my presentation. Thank you so much.
شكرا دكتور على المحاضرة الورقة العلمية الجيدة. المتحدث الأخير المهندس محمد عثمان، طالب الدكتوراه في جامعة الملك عبد العزيز قسم الهندسة الكيميائية بعنوان دراسة مركب NiO3 على هيئة البيروكسايد لتحويل غاز ثاني أكسيد الكربون إلى ميثان.
Bismillahirrahmanirrahim. Assalamu alaikum. My name is Muhammad Usman, and I am a PhD student in the Department of Chemical Engineering at King Abdulaziz University, Saudi Arabia. The topic of my presentation is study of lanthanum nickel perovskite for CO2 methanation. These are the content or agenda for my talk. First of all, I will talk about why we need conversion of CO2. Then the Saudi Green Initiative about the conversion of CO2 and the utilization of CO2. Then I will discuss little about literature review, then preparation of catalyst in our lab by Sol-Gel method, and activity test of lab prepared catalyst, and then at the last I will discuss some characterizations. So first of all, why we need the conversion of CO2. As you know that the population of world is increasing day by day, and the energy demand is also increasing. The world's energy demand is fulfilling by the fossil fuel, the conventional fossil fuel. When we burn this fossil fuel, large of greenhouse gases, CO2 and other gases are emitted in the environment. Among these greenhouse gases, CO2 is about 65%. And this is the alarming situation for the whole world. That's why research are focusing, and researcher and industrialized people are focusing on the CO2 capture, storage, and utilization. CO2 capture and storage, it is a process that is not useful as compared to CO2 utilization into some useful chemicals. But as you know, that CO2 is a very, very stable compound. We need, and thermodynamically, this is very stable, and we need a high energy molecule to react CO2. So for this purpose, we can use hydrogen. Hydrogen can be produced by renewable energy resources like solar, wind, hydropower, and then if we can bring this hydrogen to react with CO2, it can bring us a lot of opportunities, a lot of useful products. And it will not only reduce the CO2 content from the environment, but also it will give us money in the shape of some useful products. For this purpose, Saudi Arabia has took place in the Paris Climate Agreement in 2016 that they aimed at limiting global warming to below 1.5 to 2 degrees centigrade to pre-industrial level, that is 1815. And for this purpose, Saudi 2030 vision, the Kingdom of Saudi vision, is like some implementation they have started. The first one is the energy efficiency program and the developing of carbon capture technology in Neom city and in other industrial area, and increasing the public transportation. As you know that in Riyadh now the metro station and other, they are focusing on the public transportation, and also the growing the renewable energy capacity. Renewable energy mean wind energy and also the solar energy. So this CO2 conversion is in the greenhouse Saudi Green Initiative. Literature review. Why methane? Why CO2 conversion to methane? We can convert CO2 into many other compounds like methanol, methane, and olefins and lower hydrocarbons. But methane structure, methane, as you know, that methane is a main component of natural gas. So it is the system of methane is already well developed. So we don't need to make another infrastructure. The required hydrogen can be generated by renewable resources, and the CO2 methanation can be performed at low temperature and pressure. So that's why we can say that this approach is effectively killing two birds with one stone. We not only reduce the CO2 and we also produce natural gas. For the CO2 methanation reaction, this reaction cannot be take place without a catalyst. For the catalyst, we know that these are the three main properties, main characterization that a good catalyst should contain. For CO2 methanation, nickel metal is highly used because of its high activity and lower cost. But at high temperature, nickel experience some sintering and agglomeration. So the activity of nickel is reduced at high temperature. So that's why nowadays another type of material that is called perovskite material are focused in this research. Perovskite type material like oxide-based catalyst having attractive significant attention, because they have highly thermodynamically stable and movable oxygen properties, and also they are highly basic. That is a requirement for a CO2 methanation reaction. And the structure of perovskite is like ABX3. A and B are two cations, and X is a highly anion that collide these A and B. So in our research, in our lab, we prepared two type of, I have prepared 4 or 5, but this is my PhD research going on. I will discuss only 2 of them. We have prepared by the sol gel method. Sol gel method is a famous preparation method in the catalysis. For this purpose, first of all, the metal salts and the citric acid. Citric acid is used as a gelating agent, was devolved in the deionized water, and then stirred at 90 degrees centigrade for 6 hours. And when the gel-like structure appear, then we will put this sample to a water bath for more aging. And also after the aging, we will put this sample to the oven for drying at 110 degrees centigrade for about 1 day and night. And after drying, the powder sample was obtained and calcined at about 5 degrees centigrade for 5 hours. The outcome of the powder was in the form of powder. And these 2 catalysts we have prepared, lanthanide, nickel, and oxide. You can see that the perovskite A is denoted here lanthanum, and B is nickel and oxygen O is C, ABX3. And the second sample that we produce, we add some amount of 50% amount of ceria, and we can check what is the properties of the lab prepared catalyst and what are the effect of addition of this ceria. So catalyst activity test, CH4 production setup. This is the setup we performed in our lab. First of all, hydrogen and carbon dioxide, that are the main reactants, are coming into the reactor by using mass flow controller from the upper side of the reactor. We use the fixed bed reactor for this process, and then the product is collected on GC, gas chromatography, which have TCD and FID. These are the detectors, and we can detect what are our products by using the software in the computer. And these are two formulas that we use for CO2 conversion and CH4 selectivity. You can see from this slide. And after it, when we reach our activity test, these are the results by these two samples, lanthanum nickel perovskite and lanthanum ceria perovskite. At 300 degrees centigrade, at 350 degrees centigrade, and 400 degrees centigrade, we done this research at this temperature, and you can see that the CO2 conversion is increased by from 32% to 57% at 300 degrees centigrade. So when the temperature is increased, the CH4 selectivity is little bit reduced, but the CO selectivity is increased. So we need to have a higher CH4 selectivity and higher CO2 conversion at lower temperature as much as possible. So for in this case, the addition of ceria has some better activity, and it gave us better CO2 conversion.
5 minutes left, Doctor.
At the end, I will discuss some of the physiochemical properties of this lab prepared catalyst. These are the XRD phase structure, and the crystallinity of this lab prepared catalyst was done by the powder XRD. And you can see, like when we add some amount of ceria in our main catalyst, then there are some additional peaks appearing at the XRD at left side picture. At the right side, we hydrogen consumption profile you can see, and for the case of lanthanum nickel, there are three main peaks, and first two at about 300 and 350 degrees centigrade. These are the partial reduction. When we add ceria in our lanthanum nickel perovskite, then the rate of reduction or the reduction we will make easy. You can see that there is only one bigger peak in the case of second catalyst. So the hydrogen reduction is also easy in the cerium addition sample. Okay, and now here you can see that pore volume, pore size distribution of calcined sample, and also the adsorption, nitrogen adsorption isotherms. In the right side picture, at both of the sample showed nitrogen adsorption isotherm type 4, and the addition of ceria in the main sample, increasing the pore size and also the pore width. That's why the activity of this perovskite is increased by after addition of cerium. These are the SEM morphological images, and for the case of lanthanum nickel perovskite, these catalysts showed like flake-like structure, and when we add ceria, this is the random porous structure. So here all about the experimental part, and these are the conclusion that we can draw from our research, that insufficient low temperature activity and the degradation of nickel, we can use and other metal like perovskites, and our perovskites catalysts are stable and enhance the dispersion of active site. They are also the basic, and also compared to the precious metal based catalysts in terms of catalytic performance, the perovskite catalyst has efficient CO2 methanation. And this research is going on, and we are working on various further research work by variation of metal ratio and operating condition, and also the stability test of lab prepared catalyst we will do in near future, inshallah. So that's all about my presentation. In the last, I will acknowledge University of King Abdulaziz University and also the Saudi Council of Engineers that provide me this opportunity. Thank you very much for listening, all of you.
Thank you, Engineering محمد. المجال مفتوح للأسئلة. الإخوان اللي عنده سؤال بس يرفع يده يعطون الميكروفون. هنا قدام دكتور هنا.
Assalamu alaikum. Thank you everyone for your great talks. My first question is directed to Dr. Sithar. You listed a few advantages of using ammonia as a hydrogen carrier. So how ammonia is compared to methanol in terms of hydrogen as a hydrogen carrier?
Ammonia compared to
ethanol. So you will get the carbon monoxide and carbon in this one if you produce the hydrogen from the ethanol. Because why we are choosing the hydrogen why you are turning to the hydrogen? To avoid the carbon monoxide and carbon dioxide evolution completely. So for that, so we need to avoid the carbon and oxygen atmosphere. Without carbon, without oxygen, there is no question of carbon dioxide and carbon monoxide. That's why we choose the nitrogen and hydrogen. And inshallah, so we will get from the hydrogen from the water. There is also, then it will be very easy. Then we can carry the hydrogen we can produce the hydrogen from the water, and we can carry that hydrogen into the ammonia, and then we can, wherever we can go, we can transport it, and then it's fun. But right now, so there is still work going on in the electrolysis process from the hydrogen, water to the hydrogen, but still the hydrogen is producing from the fossil fuel only.
Thank you. The other question is, you mentioned that ruthenium is a good catalyst for ammonia decomposition, right? But it's also at the same time it's a good catalyst for ammonia synthesis from nitrogen and hydrogen. So how do we prevent the backward reaction?
Yeah, that is a good question. Yes, ruthenium case. In the case of ruthenium, so if you see that ruthenium is both, it will act as in both cases. You can synthesize the ammonia synthesis from the nitrogen and hydrogen, and at the same time, the ruthenium is also active for the ammonia decomposition. It has both properties. So that is yes, because it's in nature. But why we are not using? Because of cost and low availability, we are not just taking that one. But actually, it is a good ruthenium is a very good catalyst for both things. Once you have it, and one more important thing is, it won't go deactivated. Once you load the reactor, even you just use for the ammonia synthesis, and you just replace the gases, you can use for the ammonia decomposition too. That's very interesting, it was. But yeah, because we have the low availability of the metal in the earth crust and in the world, so we cannot use that one for the worldwide.
Thank you, Dr. Sithar. I have a question directed to Dr. Muhammad Uthman. Have you detected any methanol formation, methanol or formic acid formation? Because I was wondering whether you have the reverse methanol steam reforming process where you convert CO2 into methanol or formic acid.
First of all, I am not doctor yet. I am a PhD student. And secondly, you are talking about the CO2 reforming, CO2 plus CH4.
Methanol production from CO2 via reverse methanol steam reforming.
I have done.
Have you detected any methanol formation?
No, I have not done this. I am focusing only to CO2 conversion to methane. I am planning to have some reaction on CO2 to methanol as well. but right now, just CO2 to methane. I have only that.
What about the product distribution? Do you see any other products other than methane?
Only the methane and CO, carbon monoxide.
Okay, thank
Only
you.
there were only the two peaks, actually 3 peaks. One, the CO2 that is not reacted, the unconverted CO2, and the second peak of CO, and the third one is CH4. I observed only these 3 peaks for all my catalysts yet.
Thank you.
السؤال الآخر.
السلام عليكم ورحمة الله وبركاته. Thank you all of you for your valuable presentation. The question directed to Brother Saud, why you have selected the PET polymer specifically? Why you have selected the PET polymer specifically?
Because there is a kind of PET that's approved by FDA, can be used for food and medicine application. So it's more safe than BDMS biologically. So we can embed or involve this device in human tissue for medicine application or detect some enzymes, like as I mentioned, dopamine, for example.
I think also advise you to think about the PLA. PLA is well-known biodegradable polymer. However, it's well approved for biomedical related application. I have worked with it several times and published several papers in PLA, polylactic acid. Perhaps you may think about it. PLA, well approved, and I prepared a lot of experiments related to biomedical related industries. Thank you.
Thank you.
سؤال آخر. في الختام أشكر جميع الحضور، أشكر المحاضرين، وأرحب بعضو مجلس الإدارة المهندس ياسر الجهني ليتفضل مشكورا يسلم الدروع للمتحدثين. شاكر لكم جميعا حضوركم، باسمي باسم الهيئة أشكر لكم الحضور وأشكر الحاضرين، والسلام عليكم ورحمة الله وبركاته.